Professor Richard Fortey to continue today's lecture. Okay, please.
Thank you. Well, yesterday I gave two very general lectures, very broad lectures, and today I'm going to focus more down on some specific scientific problems, particularly those with which I have personally been involved. And I'm going to talk in two parts. The first part is about geography and how you reconstruct the arrangement of paleocontinents in the Ordovician period, in particular about 450 million years ago and later. Now, I have worked mostly on trilobites, also on graptolites, but I have worked over the years very closely with some colleagues on other groups like brachiopods. And so I have brought together in my own work all these different fields to try and get a picture of what the world looked like in the lower Paleozoic. Okay, now first of all I have to take you back perhaps 40 years. Thank you. To a time before it was realized that there were lower Paleozoic oceans. And I'm going to take you to an area which I know very well, and you know less well, the North Atlantic region, including where I come from, the British Isles. Now this is a map taken from my old professor, published about 1970. And it shows the North Atlantic region as it was at the time of Pangaea. Because at this time, it was not realized that there were oceans, Paleozoic oceans, earlier than Pangaea. So we have North America here and Europe joined together as one continent. But at that time, it was already realized that the trilobite faunas and other faunas in different parts of this area were very different at the same time. So, for example, in this area, which we would now call Laurentia or North America, the trilobites were different from the areas on this side of the Atlantic. So I'll show you. No, I won't show you. I will show you. In North America, for example, there were trilobites of this family called Biogeography, which are extremely abundant everywhere in North America and in Greenland, and indeed in part of Britain. But that part of Britain which is in northwest Scotland, the northern part of Britain only. Now, just to show you, just to go back. No, just to go back. You can find these sorts of trilobites here, for example, in the northern part of Britain, but also here in Greenland and very widely in North America over in this area. But if you go southwards into Europe and North Africa, there are very different trilobites, completely different families even, which include, for example, genera. I'll mention a few names, not too many, like Nesuritus, which is known here in China, and other particularly members of the Phacopidae and related families. So they are quite different, but how do you explain these differences? Now, the simplest way to explain formal differences is by oceanic separations. After all these trilobites lived under the sea, and if they're close together, but very different, then the implication is that they were originally far apart, separated by an ocean. Now in 1982, my old friend Robin Cox, who's an old friend of this institution as well, and I made some principles for deducing, for working out and understanding ancient geography using fossils. And these principles have, although they are quite old now, I think have survived the test of time, as we say, very well. So what you must understand now is, imagine you have two continents which are separated by an ocean. This is the top diagram. And those two continents are of the same paleolatitude. I've shown it here as equators, as at the equator. Now, if you have faunas on a continental shelf, if those distances are not too great, you can still find similar faunas living on shallow seas here and shallow seas here, if they are able to disperse between the two continents. Because the conditions for living here will be similar to conditions for living here. On the other hand, if you have two continents, paleocontinents of different latitudes, say equator and far to the south, then the conditions on the shelf here will be very different from the conditions on the shelf here, and the same trilobites cannot live. This is when you will find different forms living here and different forms living here, and you can infer, think about the presence of an ocean separating the two forms. On the other hand, deeper water benthic faunas, like on the continental slope, will be often similar even on the other side of quite wide oceans, because the conditions for life are very similar here and here, beneath the thermocline or at depth in the ocean. That's a very simple set of principles for working out ancient geography. So, if I can return very briefly, yes, to this map. In this area we find shallow water Biogeography, which are very different from all the trilobites in this area, even though they are close together on this map. So we infer that originally they were separated by an ocean. Okay? And that led to a series of maps. This is a more modern version of the same principle, in which I have introduced 3 dimensions, and this is quite recently published, and also another complication which I will talk about, which is the presence of islands between two continents. So here we have shelf endemics, here we have shelf endemics, and if they are of different latitudes, paleolatitudes, they will have different species. The islands are something else, which we will come back to. So, let's go on. This is going back to the original map, but now putting in the faunas and inferring the separations. So you see, here is the Bacchiurid area. There you'll see Greenland, characterized by those particular shallow water trilobites. Down here, the pink are where the Palaeontology trilobites, the other high latitude trilobites, are found. And in green here is a third set of shallow water trilobites, which show that the Baltic continent, and here you will see the Baltic area, known as Baltica, was a third set of trilobite genera, all living in shallow water. So what we started with one continent, we now have 3 separate continents. And between them, we have oceans. The widest one was called, and has been known for a long time, as Iapetus, which separated North America in the Ordovician from Baltica here, and from what we will call Gondwana down here. We also, Robin Cox and I, proposed a sea separating Baltica and Gondwana, we called Turnquists, after a famous line, geological line, although it was initially resisted by some geophysicists, subsequently the existence of this ocean has been regarded as accepted. And this was based entirely on formal evidence. So those are the shelf faunas. Here, 3 different shelf faunas, and the brachiopods are also different, not just the trilobites. I'm going the wrong way. As far as the plankton is concerned, and that of course includes graptolites, floating organisms, they are also different because they are all at different latitudes. And the main control on plankton in living oceans and in old oceans was paleolatitude. So here you have low latitude plankton, here you have intermediate latitude plankton, and here you have high latitude plankton. But the graptolite story is a little more complicated than that. I may have time to explain. Now, I also mentioned lithologies and deep water faunas. If you look just at the rock types, they are also different in these 3 areas. Near the equator, we have shallow water limestones in the shallow water areas, surrounded mostly by a deep water shales. At intermediate latitudes, we have temperate latitude limestones in the early Ordovician, this is, surrounded by deeper water shales, and at high latitudes we have only clastics, sandstones, and similar rocks, but also surrounded by deeper water shales. So the second part of recognizing ancient continent distributions is to recognize deeper water biofacies, or facies, surrounding the shallow water. That's another part of deducing ancient geography. So we use faunas, we can use lithologies, and we can use inferred water depth to arrive at conclusions about paleocontinents. So you can take this much wider now. The piece I've been talking about of Britain, of England and Wales, lies just on this corner of, I said, the great Gondwana paleocontinent at this time in the Ordovician. But similar shallow water faunas, identical in some cases, even species, are found over a huge area of Gondwana, of Ordovician Gondwana. But this is such a large paleocontinent, it goes everywhere from high paleolatitude near the pole, which was actually here in northern Africa, all the way down to China and Australia, which were at nearer tropical paleolatitudes. So this is one huge paleocontinent. The green shows the high latitude or cold water faunas. This symbol over here shows the more tropical faunas, and because this is such a huge continent, and as you would expect, there will be mixed latitude faunas or oscillating faunas at intermediate latitudes. This is an old diagram, but it's still broadly true. So through the Middle East, sometimes you find Chinese style, sometimes you find what I will call European style and African style faunas. So you can do, this is a climb, of course, across a single paleocontinent. But all the way around the edge, shown here in stripes, we can find deeper water biofacies and graptolitic facies, which serve to define the edge of this great Gondwana continent. Now that's the simple picture, because it divides the world into a very few, very large continents. I've mentioned Baltica, I've mentioned Laurentia, North America, and now this great Gondwana continent, including your own country in the Ordovician, which includes much of the rest of the world. So that is the simpler picture. There are, of course, complications, particularly in the Ordovician or in the Paleozoic as a whole. There are changes in sea level, transgressions and regressions. And one of the effects of transgression, of deepening water, is to bring the deeper water faunas that lived off the edge of the paleocontinents onto the shelf at certain times. So that's a low-level stand, if you like, raise the sea level, and certain kinds of trilobites and graptolites, which normally live in deeper water, will appear on the continental shelf. These are very useful events for international correlation, but sometimes more widespread faunas appear at deeper water phases, which sometimes people have misinterpreted for paleogeography, because the faunas can actually be quite similar on different paleocontinents at deeper water times. So that's the first complication. There are many more. You can, of course, if you wish, and this is an old example of mine, apply various clustering techniques, statistical techniques, to measure similarities of faunas. This is, I think, this is a method based on cladistic analysis, which gives you some bootstrap support, strength support, for different clusters of localities. In this case, for example, just a very simple example, Brittany, Spain, France, Bohemia, Lake District, and South Wales, stars here, are the Gondwana group, which all cluster together with high support. That's one paleocontinent. Sweden, Latvia, Bornholm here, very high support. One other cluster, that's the Baltica continent. And this lot in the middle here, with not quite such high, well, no, actually very high support overall, is the Laurentia paleocontinent. There are many different techniques. I won't go into these in detail today. That was another form using acritarchs, showing that they are not as good for resolving paleogeography. We have very low support for some of these branches as the trilobites. So trilobites, brachiopods, very good for doing biogeography. Acritarchs may be better for doing stratigraphy because they are wider spread. Then, of course, different organisms have different ability to spread from one continent to another, depending on their larval development. If you have a larva that lives a long time in the plankton, it can spread wider. And in general, most people here, most specialists in your institute would agree with me, I think, that conodonts, nautiloids, and graptolites particularly are widespread. Graptolites, of course, spend all their life as plankton, whereas things like corals, cystoids, and bivalves, which develop very quickly, are not good for international correlation and very good for doing local biogeography because they don't move around much. So you have to put all these things together in your mind. Just to show you how widespread some genera are in acritarchs, this is I'm mostly talking about the early Ordovician, just to make matters simple, I should explain. This is the distribution on Ordovician geography. That's the Gondwana side here, and that's Laurentia and Baltica there, and that's a Siberian plate of one acritarch genus. This is taken from the work of a colleague of mine, it's not my work, showing how widespread acritarchs can be. And you might like to compare that with some very more narrowly distributed acritarchs, which will give you at least the difference between Baltica and Laurentia and Gondwana here and here, but won't distinguish further between Baltica and Laurentia. Anyway, that makes the point that not all fossils are good for paleogeography, or some are better than others. I've talked as if, of course, the continents were fixed in position during the Ordovician. They weren't, they were moving. In particular, the Iapetus Ocean closed throughout the Ordovician, or got narrower throughout the Ordovician. And one of the things you can do is plot the changes in ocean distribution by the changes in fauna. This is just happens to be an example from trilobites and brachiopods and other organisms. In the early Ordovician, at about 480 million years, this is the distribution I've already mentioned, with Bacteroids, certain kinds of asaphid trilobites here in Baltica, and a different fauna here in Gondwana, just that part of the North Atlantic. But by the time we go through 20 million years, some things have changed, and in particular, a microcontinent, a small continent we know as Apollonia, has broken away from Gondwana and is drifting across enclosing hiatus. And this is reflected in changes in the faunas on that microcontinent. I'll come back to this in more detail. Just to show you on the original map again what it looks like, or probably looked like at the time, you now will recognize Gondwana, Baltica, and Apollonia, but between them there were oceanic islands. This is an old slide of Bob Newman's, I think. These were islands within the Iapetus Ocean, volcanic islands, which also had faunas. And they themselves will have a special biogeographic signature. So the world was just as complicated in the Ordovician as it is today. Continents, islands, oceans. It's easiest to start with the continents, because they give you the best, most secure signature, most secure identity, and then move on to the islands. But people have spent a lot of time worrying about islands. But again, one can have some principles to determine where an island or microcontinent was. So, here we have some different cases. Now, these are lines of paleolatitude, okay? And as we've seen already, paleolatitude is the most important control on biogeographic distribution, and bioclasses as well. If you have a microcontinent or an island, say here, which lies off a continent which I'm calling A, if that has a shallow shell fauna, and that has a shallow shell fauna, and that is a moving microcontinent, and moves along the same line of paleolatitude, you will not pick up that movement by faunas, because it will simply be moving at the same distance away from the larger paleocontinent. It will have the same fauna. So that's the first case. In case C, which is rather like Laurentia and Gondwana, imagine now you have an island which is halfway between two paleocontinents at different paleolatitudes. Say this was on the equator and that is near the pole. There is then the possibility of these faunas in the island being half like that and half like that, intermediate, because they can be recruited both from there and from there. But of course, because they are separated, you might also find some endemics, only found on that island. Okay? There are other cases too, which will take too long to explain, but those are the two extreme cases. This one you cannot say much about position. In this case, you can more or less precisely say where a paleo island or microcontinent was by looking at the faunas. This perhaps is rather too elaborate to explain in detail. It is not surprising that with different methods and different people approaching this and using different computer programs, you arrive at different solutions for the geography of ancient times. These are three different time slices through the Ordovician to the Silurian by two different authors. A.B. Smith on the left and Chris Scotese on the right. These are mostly computer-generated reconstructions using all sorts of different evidence, particularly paleomagnetic evidence, which is independent of the fauna evidence, which is very good. But the faunas can be used to say which of these two types of reconstruction is most accurate, which is better. The faunas can provide a test for tectonicians, in other words, to keep them honest, I would say. because some people would like to say that their reconstructions are entirely correct, and you need the faunas to test, or fossil faunas to test whether or not one particular reconstruction is good. I won't go into detail here, but with a student of mine called David Leese, we evolved a taxa-based method for assessing the position of small plates in relation to major paleocontinents. That was the formula. This is one of the results. Now, I've already told you about Apollonia, this microcontinent, and its movement from Gondwana across this closing Turnquist Sea to engage and meet with Baltica. And this is this microcontinent at one particular time in its movement, the Irenic, which I have particularly worked on, early Ordovician. And in fact, what we did with this method was to combine all the formal data, which is a lot, from all this area shown on the map, take the positions of the main paleocontinents, which are well known, okay, these paleocontinents, put all the formal evidence together, and then find the best solution on the formal evidence for the mixture of things that we found in Apollonia. So it's like that case with the island in the middle of the ocean. We know this is somewhere in the middle of the ocean, but where? It has some elements from here, it has some elements from here, it has some endemics, and in fact at this time it has virtually no elements from here, which gives us an optimal position between Baltica and Gondwana and far away from Laurentia, and this is its best fit position. And in fact, we can then compare with the two previous geophysical reconstructions and see which one it is closest to. This is entirely independent evidence. It turns out that Scotty's and his reconstruction is better than Smith and his reconstruction. There are other ways of doing it. This is work by somebody who may be known to some of you here, Sam Turvey, who was my student in conjunction with Professor Geology. And Sam studied in great detail one particular group of trilobites which are typical of the Gondwana continent. He made phylogenies, that is evolutionary trees. This is one of them. And then on this he mapped the geography in which the various species, this is a species level piece of work, on which the various species occur. Well, oops, wrong way. This is substituting places for taxa. And in this case, he found various subgroups of relationships within this particular group of trilobites, which indicate sub-regions within the Gondwana continent. For example, down here, we have a kind of Western Avalonian France, North Africa group, characterized by common and related taxa. So you can bring many different methods to bear if you're going to try and deduce something about ancient geography. This is the map that won't appear. That's a shame. Try the next one. It's appeared. Now, another critical test. This is a paper by a very clever Turkish geologist called Celal Şengör and his Russian colleague Natalin, published not very long ago, which reconstructs that middle part of Europe, of Asia, in relation to the Russian, Chinese, Tuva-Mongol arc and Angara cratons. This is a very complicated geology. It's that bit in the middle of Asia, we'll see it on the next map, I think, where, let's go there now. Yeah. No, I'll go back. Now, the point is that this is their tectonic reconstruction of what the Asian complex looked like in relation to the Russian platform and other areas in the Ordovician. Basically, they had the whole of Tuva, Mongol Arc, Kipchak Arc, and various terrains around Central Asia ranged between the Russian platform and Siberia, in one great big island arc. When we looked at the faunas, however, it's not such a precise map, we found that many of the faunas that make up the terrains in Kazakhstan and other areas actually were more like Chinese faunas, not like Siberian faunas, which resulted in a map which is actually quite different, in which we say that Chuili, various Alpan Sayai, and various of these terrains which they arranged in a single arc connecting Siberia with Baltica were actually more likely to be near to South China, Tarim, and Sibumasu, which is the Malay Peninsula, essentially. This was just based on faunal differences, but tested their tectonic reconstructions. So returning just briefly to this principle again, what we found was that these terrains, these small areas, if you like, mobile and in the oceans, were mostly like one side, which was the Chinese Tarim side, rather than the Baltic Siberian side. So we're able to put it closer to this area. And it really is, this is what it looks like on the ground. It's an extremely complicated area. And in fact, the faunas themselves define the tectonic and stratigraphic units into which this area of Central Asia can be divided. I've outlined them here. This is not my work, this is mostly Robin Cox and his colleagues' work. And there's another one. And this demonstrates the similarity of some of the genera that are found in the Kazakhstan assemblage of plates in the center of Asia and in common with South China. You will probably, these are brachiopods, so you'll probably know them better than me. But they include things like Yangtziella, the name says it all, and various other genera familiar from South China, which are also found in some of these Kazakhstan terrains. But you see there are also some genera in common between Kazakhstan and Australia, also at low tropical paleolatitudes. Very few actually in common with North China. This is for the Ordovician. And that's what some of these rocks look like in the field. Well, you can read these. So this is all about grouping the terrains in Kazakhstan according to their faunal competence. Now, they've not only done that, but they distinguish between Western and Eastern Kazakhstan terrains based on their faunal complex. Okay. I'm going to return now to briefly to Abylonia, okay, which is this microcontinent, which includes the southern part of Britain and a sliver of terrains which run through Newfoundland into the Carolina slate belt on the edge of North America. Now, this has been regarded as more than one terrain. It's been divided into east and west Apollonia regarded as two separate terrains. But if you use the polar wandering paths, they are identical on east and western Apollonia, and we regard them as one single terrain. We can then look at the faunas to see how they plan out. Now, I told you already about Apollonia in the Ordovician and how it moved from one side of the Iapetus Ocean to the other side of the Iapetus Ocean. In the Cambrian, it's something of a problem, and we've only just really looked at this because it seems to have a tremendous mixture of all the different terrains around the North Atlantic region. Here we are. I've just broken the trilobite faunas from Apollonia into their components, and it's a mixture apparently of some Laurentian, some Gondwanan, and even some Baltic taxa. So this would imply that it was somewhere in the middle of the ocean again. However, when you actually look at the faunas in detail, you find that the majority of the similarities across all the different paleocontinents are because of a number of rather distinctive genera. And here they are. And you'll notice that all of these are blind trilobites, okay? No eyes. In fact, although they're called conocorophids, another student of mine showed that they've been derived from a number of different families. Polyphyletic group of blind trilobites. These are actually very deep water trilobites. And like many deep water trilobites through geological time, they lost their eyes. And most of the similarity between, the widespread similarity between these different terrains for the Apollonia continent at this time is due to the widespread occurrence of these deep water blind trilobites in more than one paleocontinent. So this is the complication I mentioned before about widespread deep water trilobites being more widespread than the shelf trilobites. So when you reanalyze the data, taking out these deep water trilobites, you find that there is a much stronger signal relating that Apollonian terrain in the Cambrian to Gondwana rather than to Laurentia or Baltica. So you have to be very careful about how you use the faunal data if you have deep water facies there too. I think Wandong it applies to graptolites. Some deep water graptolites are very widespread. Some shallow water inshore graptolites are really quite local. Now, at the same time, I've mentioned that in the islands, when an island is separated in the middle of an ocean, it is quite likely that endemic species and genera will evolve there, just because of separation. And for those organisms which disperse very slowly, like brachiopods, it's more likely to find endemic species. This is an example, for example, of a mid-ocean island which now is found in Norway on the western side of the Iapetus. These are all endemic genera described by Bruton and Harper some time ago, which are only found on one or two islands. Oh, I'm sorry. Well, they're a mixture. That's cosmopolitan taxa. Those are the Laurentian taxa and Baltic taxa there, and the endemic taxa are there. So this is a real mixture for that particular fauna. Where they have been collecting on these islands, the faunas are also extremely rich. So they collected quite a number of taxa some years ago, and they've continued to collect over the last 20 years, and the number of taxa they're collecting with their samples are still rising even today. So the implication is that there's very high diversity but very low density in these sort of island faunas. So brachiopods for the Celtic province, these island faunas are particularly characterized by endemics that are found only in those islands. There we are, Celtic faunas by a large number of endemic brachiopod taxa with some cosmopolitan forms mixed in. Finally, we have to insert another complication, which is changing climate. And this is something I've worked on myself. If you accept the geography that I've described, what happens if you suddenly warm the climate or change the climate in some kind of way? Recall the original picture. You have some faunas which are cold water faunas at high paleolatitudes. You have other faunas which are warm water faunas around the paleoequator. Now that's with big climatic zonation, as we know was the case in the Ordovician. But what happens if you have a phase of global warming? Well, originally you will have carbonates, for example, forming only near the paleoequator. If you warm the climate, the carbonates will move towards the pole. If you have taxa which are normally near the equator and you warm the climate, they will be allowed to move towards the pole. If you have higher temperatures near the paleoequator, remember we've now moved warm water taxa towards the pole. If you get higher temperatures at the paleoequator, you will get exceptional and unusual conditions at the high latitudes. At low latitudes, near the paleoequator. So you will get endemics appearing adapted to extra high temperatures around the equator. But, on the other hand, these deep water biofasces, the ones which are widespread, will not be affected by changes so much in the surface temperatures, and so will be largely unaffected. Now, there is some evidence in the Ordovician for a very important warming event near the end of the Ordovician, which I call the Boda event, where you can see all of these events happening. And some will involve some Chinese taxa, so they're of interest to you in particular. This is a genus called Ogolocephalus, which has virtually all of its history here in China. And Professor Zhou Yi has provided a very good account of the history of this particular genus in China. The point is it goes virtually all the way through the Ordovician. In fact, you showed me, I think, the earliest species of it the other day. So this, as I've explained, is a particular genus which likes to live in quite warm water, particularly in the eastern part of Gondwana. But at one point, late in the Ordovician, it moves out of that area where it has been living very happily for tens of millions of years and moves in very widespread through into Europe. On the other hand, here is an animal called Heliomera, which lives in the tropics in North America. It may be here in China, I'm not sure, but it's very characteristic of Ordovician rocks in North America, which were also on the Paleotropics. But they stay there for a long period of time through the early Ordovician, tens of millions of years. That's an example of a related taxon on the right from North America, and on the left when it suddenly appears in Sardinia, in a former cool latitude in the late Ordovician. It is actually a particular phase during the Ashkule period in the Ordovician. Now, the way I explain this is by a very quick period of global warming late in the Ordovician. So there's our fundamental geography, Laurentia over here, Gondwana over here and the warmer part, including China, over here. And at this particular time in the Ordovician, because of global warming, these taxa can move towards the pole. They move from America towards the pole, and they move from the eastern part of Gondwana towards the pole. Very suddenly they appear in rock sections in Europe where you have no hint of them before. There are also special things that happen to the brachiopods at exactly the same time. For example, in the Boulder limestone, there are, now that is, I should explain, a warm water fauna to start with, so it gets still warmer during this time of the warming event. There are some genera which are familiar from China that appear there for the first time, and others which become endemic at that particular moment in time. There are some examples of these. These, I think, are endemic ones to the Boulder limestone that my friend Robin Cox described, one of them named after Professor Rong Jiayu in this institution. At the same time, North America, which was tropical, of course got even hotter during this period of global warming, so that the tropical genera are moving towards the pole, but it gets even hotter in the center of America, and so endemic forms appear there, very short-lived. This is a coral called Growinkia, which is very widespread in the center of North America during this period of global warming. And I believe that some very strange graptolites which appear here on the in China, like Tangiograptus and so on, which are known only from this one area and from this very short time, are probably also endemics that appear in response to this very brief period of warming. At the same time, there are trilobites living in deep water which are completely, or apparently completely, unaffected. Now these groups are, you'll hear more about them later, but they're one of my favorite groups of trilobites which were pelagic, which had very big eyes, and which lived probably at some depth as mesopelagic animals in the water column. Now they appeared in the early Ordovician, and they carry on all the way through the Ordovician, more or less unaffected by this event of global warming. They're in fact the most conservative of all trilobites, even though they are very highly specialized. And then, of course, we have finally, at the end of the Ordovician, we have another event, which is that of dramatic global cooling. And that too overwrites the earlier biogeography. For example, this brachiopod Paramalomena is enormously widespread, where it accompanies the glaciation event of global cooling that followed on after the global warming at the end of the Ordovician. And anybody that works on trilobites will know this animal, Mucronatopus mucronata, which is found almost everywhere in response to a dramatic cooling that followed on the warming. And this is a world map of Ordovician geography showing well, absolutely ubiquitous, occurring everywhere, occurrence of this particular trilobite species. Now this climate event was so important that it overrode almost everything I've been talking about before. It destroyed a lot of the faunal differentiation between one part of the world and the other, and in fact the tropical area was confined to very small relics in this sort of region here at this time. And the global biodiversity index, variety of fossils, fell enormously during this very brief period at the end of the Ordovician. Well, it's rather a complicated mixture of elements, so I hope I haven't confused you too much. I think the important thing to remember is the distribution of shallow water faunas on paleocontinents, relatively shelf faunas, give you a very, very good fix for biogeography. and indeed for paleolatitude and for rearranging the continents. The minor continents, terrains, islands, and so on, have to be placed relative to those major continents. It's very important to distinguish the bioclasy, the depth at which organisms live, because that too affects their distribution. If you want to make good inferences, ideas about where a particular continent lay, then it's a good idea to use the inshore and more shallow water faunas. Because the deeper water faunas will be more widespread and not give you such an accurate fix. On the other hand, if you find deeper water faunas, really deep water faunas, then it's very good for identifying where the oceans were, because you only find the deep water faunas in the oceans. And finally, the whole story can be complicated by climate change, which can shift faunas from one part of the world where they are well established to another part of the world. But that is recognizable as a bio-event. Usually the sudden appearance of a taxon or brachiopods or a trilobite or even a graptolite that is well known for a long period elsewhere and then suddenly makes an appearance in a different paleolatitude. Okay, well, this is due not just my own work, but to many of the other workers who work on things that I don't, like brachiopods. And the other thing I want to emphasize is that to get the best results, I think you use a combination of not just trilobites, but other organisms, brachiopods, and graptolites together, which makes an institute like this particularly good for it, where you have specialists in different groups all working together under the same roof. Sometimes people make much too much of the evidence of one particular taxon. They say, I have found one trilobite here, maybe in Mongolia, which has previously been found only in, let's say, New Zealand. And that shows an affinity between Mongolia and New Zealand. Well, you can't do that. You have to work on whole faunas, and you have to preferably work with different specialists working with different groups and put all the evidence together before you start drawing ancient paleogeographic maps. And that, I think, is all. Thank you.
Thank you, Richard. This lecture gives us many very general aspects on geographical reconstruction. Also give us some case studies. So, for discussion time, for several minutes for discussion.
Yes, if I didn't make something clear, particularly to you younger students, please ask me.
Oh, okay. Okay, first of all, students.
As a regenerated younger student, could I ask you where the relic tropical faunas were? I missed it on that.
Oh, right.
Slide.
Yeah, there are some. Yeah, there was, of course, a mass extinction at the end of the Ordovician, mostly as a result of these rather dramatic climatic shifts, which also affected the oceans very greatly, particularly oxygenation in the oceans. There were, however, some tropical faunas which survived in places like Anticosti Island in northwest Canada. So there were the central part of the tropical belt and little reef structures and so on continued through this climatic crisis.
Do you get evidence during the extinction? Is that the extinction, and then do you get them again afterwards?
Well, you can map the extinction event, but some of the things that pass through the event are found just below it and also just above it. And then there's another point. Do you remember Jablonski's term Lazarus tax? Some things disappear late in the Ordovician, and then you think they've gone extinct, and then they reappear somewhere up in the Silurian. So they must have gone somewhere in a refugium in order to reappear later on. But there are some surprising results. For example, I said about the those deep water trilobites being more or less unchanged throughout the Ordovician, which I think is true. But they do go extinct. They're the ones that go extinct at the boundary, at the Silurian boundary. No cyclopygids survive it. Now why? The only explanation has to be that forms that were living in the oceanic area had a crisis because of, I think, probably very widespread anoxia in the oceans. They've been living there. Some of these things have been there since the Cambrian. Agnostics, for example, small blind trilobites, come all the way through from the Cambrian to the end of the Ordovician, and then they go. Most of the graptolites went, and they were, of course, the oceanic. Few, 3 or 4 taxa only survived to repopulate the Silurian. So the extinction event, when it finally happened, was oceanic. And the survivors, ironically, were epicontinental, or a majority of them were epicontinental, living on those shallow shelves, which gave rise to what happened in the Silurian. And another example, many of the deep water trilobites, right from the Cambrian, which are blind, went right up to the top of the Ordovician, and then all of those went. And in fact, you have to go quite far up in the Silurian before you start finding some of these deep water trilobites that went blind again. So it's a very interesting and complicated event.
Very interesting regarding plants in the late Paleozoic to the Trias. Very similar.
Very similar. Of course, the plants were just getting going in the middle Ordovician.
Yeah.
And probably found the conditions at the end of the Ordovician quite testing.
Yes.
So it went on.
Sorry.
It's very interesting that you mentioned that shallow water fauna is more strongly affected by the global warming, and the deep water organisms are less affected by the warming, and this is quite interesting, especially the trilobite example, also probably the graptolite. So what's the mechanism behind this difference between the shallow water organism and deep water organism?
Well, my view of it is that as you go down into if you go off the shelves down into the continental slope, you are, regardless of you are going down in temperature, right? It's getting cooler as you get deeper in the ocean.
Yeah.
So the most affected by global warming are the shallow oceans, particularly in the tropical areas. But if you go to the right depth, you can find similar conditions throughout the crisis, throughout the warming interval. So, for example, the Pholiomena fauna, which is a brachydont fauna, is found all over the world at about this time. So it is the shallow water faunas that tend to be more severely affected. But if you have something like the Yangtze platform, very widespread area, then the whole platform probably was subject to this elevated temperature. And this is when these strange multi-stite Tangaia and its relatives evolved, only confined to that area. Although recently I think it's been discovered in North America, one of this family, which by Alf Lentz, which is also one of these elevated temperature areas. So yes, I think it's true to say that the inshore faunas are affected more. Across Gondwana, they were very free to move, because we've seen it's one huge continent. They were very free to move. So they probably, if temperature rose, the whole fauna from China, I think, would move towards Europe. And there are other genera, Alatella and so on, that occur in the same interval. It's not just, what's that thing from Pagoda limestone? Very, very strange and distinctive trilobite, whose name I've forgotten for a moment. Paraphyllipsina, very, absolutely distinctive. Suddenly appears in Sardinia. Never before, none of its relatives before. If you found just one thing, you'd say, oh well, it learned to live in new conditions. But if you find a whole fauna that's moved, then I think you involve the climatic change.
Yeah, also a second question. I think most of Chinese are not very familiar with the Avalonia,
Yes.
the continent. I think, and then
I'm
in
aware
the
of
region, it's a terrain of a microcontinent, but later separated by the Atlantic. You know.
Yes.
Can you explain a little more?
I'm aware when I talk to you, it's very hard to explain everything to you in the way that I would like to, or it would take me all day. Yes, the Avalonia microcontinent is a piece of Europe and North Africa, which includes the southern part of Britain, which is quite controversial because it includes, obviously, the type Ordovician, the first Ordovician. Where was it during the Ordovician is a very important question. Now, there have been many, and there still are, many different theories about when this microcontinent, Avalonia, rifted off from Gondwana and went across that Iapetus Ocean. Some people think it started already in the Precambrian, Ed Landing, for example. Other people think that it happened quite late on. So we went to the faunal evidence to see if we could find a critical time when the fauna started becoming different and distinctive in Avalonia. And the answer is, in the Arenic, we still have Gondwana's signature. Trilobites, Nesuritas, for example, things well known in the Gondwana continent. But we also have some endemic forms which appear only in Avalonia, already by that time. But mostly it is still a Gondwana signature. By the middle Ordovician, however, we have Baltic and North American forms which are appearing. So we know we are now in a separate existence. There is an exactly similar argument you can apply to South America for a big terrain or microcontinent called the pre-Cordillera terrains. Yeah. I didn't talk about it today because there's too much to say. But that, at one time, is like North America, and later, in the early Ordovician and Cambrian, later it is like Gondwana. So it changes from one to the other.
Another direction.
Moving in the other direction, exactly, yes, yes. But the fossils are extremely useful, and sometimes uniquely useful, in saying, at this time, where was this microcontinent? But at the same time, you have to be very careful how you use the evidence, because it is very easy to make a mistake. For example, in the deeper water Avalonia, there are some trilobite faunas which are quite widespread. Olenid trilobites, which I didn't even mention. Olenid trilobites, one particular family, can be found all around the world in deep water facies. But when people found them, they said, aha, we have a similar trilobite here to one in Newfoundland. Perfectly true. Therefore, Avalonia was near to Newfoundland at that time. But that's wrong, because